Hello everyone. Today I'm going to talk about something which is at the heart of distributed computing. It's called CAP theorem. While it is very important, but it intimidates a lot of people who are new to distributed computing, and sometimes it's also very confusing to the people who are at least starting with distributed computing. So I thought it will be a good candidate to start looking into because I'm doing a series of talks on distributed computing. So I thought I'll pick up that. And as always, what I'll try to do is I'll try to cover it with with an example that you can very easily correlate with. So very quickly, Mr. Eric Buer, a well-known computer scientist, he's the guy who gave this CAP theorem. So we'll dwell into that CAP theorem, but we'll start with something where we'll kind of park aside what is CAP theorem, etc. And then we'll start with something that you can correlate it with you first, and then we'll delve into how CAP theorem impacts that and what it talks about. Okay, so having said that, let's get started. Um, let's imagine that there are two college students, two friends, John and Chris, and because they are friends, so they go out for entertainment together, and because of that, sometimes they lend money to each other. So they want to kind of keep record of who has lended how much to other person, so that of course they can balance as well from time to time. So here, this is what I'm showing here. So from John to Chris, £100 lend on this date. So very simple structure, very simple. And they are computer science students, so they said, okay, yeah, we can easily write a program around it. I mean, this is again a hypothetical example, but just to give you some context so that you can start thinking about it. So they wrote a simple program around it, which queries this file and answers simple questions like how much Chris owes to John, something like that. So yeah, so that program is running on a server with a file on it. It's very simple setup. Now let's just imagine that this program all of a sudden became popular. Everybody in your university wants to use it and all that, or whatever reason you decided to say that, okay, let's have another server so that we can answer more and more queries and also keep redundancy, keep another copy of this file and this program running on that machine as well to answer the query. So now you have got a simplest of simple distributed system. You have a program that runs on these two servers, and you have some state that ideally needs to be maintained on each server. So that state is the information as to who has lent how much to other person. So that file, that state, that information is on server one, and to be able to answer the queries on server two as well, you need to have that same state here as well. So this is what now this computers, these servers are connected through some networking. So yeah, and then the client can ask questions. And the idea is because it is a distributed system, again, I would encourage you guys to also have a look at my previous video where I'm introducing distributed systems. But yeah, because it is a distributed system, so ideally you want to end up in a situation where client can go to any of the servers. It can ask this server or that server about its query, and then server should be able to answer that query. And the client shouldn't be forced to go to a specific server. So this is something that we want to aim for. So let's drill into this and see what we get into when we start expanding onto these things. So very first thing, yeah, an entry is made from the client machine, which will say that John has lent to Chris £100, and then we put some timestamp in there as to when it was done. Now, as soon as this entry is made in here through your program, now your program will ensure that, okay, this information is what we call replicated in a distributed system. But yeah, end of the day, think of it like a simple, on a very high level, you can think of it like now that new file is copied from this server to another server because you want to keep the same state in here. So information added here and then copied over to here. Now, if the client asks after writing it here and before this file has been completely copied, if the client's, after the file has been copied, when the client asks the question to server 2 as to how much Chris owed to John, it will get back answer 100. And then if the same question is asked on server 1, of course, it will get back the answer 100. So what we are saying here is these state, this information is consistent across both the servers. So we have consistency in there. So they both are saying the same state. They both are saying the same information. So now whether clients ask question to server number one or to server number two, client is going to get back the same answer because they are consistent. The state on the servers are consistent. Now let's look into a bit more. So let's say, I don't know, on 3rd Feb after a few days, uh, uh, Chris has returned some money, right? So Chris has returned, uh, let's say 60 pounds to John. So again, this information through this client is being written, let's say again on server one. So server one has written this information in here. And when it tries to replicate this information, some error occurs, some network. So the error occurs, and the means by which these two systems were connected to each other, that means is down for some time or there is some issue with it. So now it can write it here. Server one can write it here, this program can write it here, but this information is no longer, at least at that point, in a state where it can be replicated or copied over to server 2. So now imagine what are the possible scenarios and what can happen. So if we say that server 1 goes ahead and completes the request of writing here, and after that, if clients asks a question to server 2, how much Chris owes to John, then the net answer on here, because the state that John, this server 2 is saying it doesn't see this second row, it only sees the first row. So it will still say 100 points. Whereas when you ask the same question to server 1, it will say 40 pounds because part of it. So now it has got another piece of information. So here it will say that 40 pound owned by Chris, and here it will say that 100 pounds owned by Chris. So now the two servers are giving different answers, and this is where we are saying that the servers are not consistent with each other. The information that they have got, it is not consistent with each other. So let's put it this. So now we have talked about few things. We have talked about consistency, and we talked about that now that consistency could go out of sync, or it could become inconsistent when servers cannot communicate with each other. Now another important thing here is that availability. So again, look into that same scenario. uh, so if I again say that we were trying to write this second row in here, it can be written onto server one. So client can still communicate with server one, but there is some problem in communication between server one and server two, and it cannot write this second row onto server two's local file. So in this case, now if you think about it, we have two choices. We can write it here, and then we can somehow go into a model where we can say that client can only ask questions from me. So before they, as in, they should not really go to server 2 because server 2 is now kind of like inconsistent. So that before this situation, we were saying that we have two servers and they are kind of like peers of each other. They are pretty much at the same status. Client can go to anyone. Now we are saying that, okay, client should not go to server 2. So it's kind of becoming a master here and saying that now I am the only one and I don't want client to go to. So that is one approach that could be thought of. And that is where what we are doing is we are kind of sacrificing the availability. So now both the nodes are available. What we are saying is because of this problem, we are saying that now you can get into a situation where you would like to say that only server 1 is available, server 2 is no longer available, because you know that from server 1 some information could not be replicated to server 2. So you are saying that only server 1 is available to serve the client request, but server 2 is not available. So here we are talking about the concept of availability. So basically what we have seen is we have talked about few concepts here, and now let's jump to CAP theorem. So we talked about few concepts. What are those concepts? Consistency. So we said that uh, in a normal running state, in a normal running setup, this state is consistent across two, which means that no matter where client goes, they will get the same answer. So that is what is complete consistency. Um, then we talked about availability. So cluster as a whole how long it is available. So we are saying that in certain scenarios we have two choices. We can either leave the cluster as a whole available to the client, or because of certain situations like we talked about, this message could not be replicated, we can say that the only one node is available. Like in this example, out of these two, one is available. In this case, this is only available and the other is not available. And then we have partition tolerance. So when we talked about this scenario, when we said that these two nodes cannot communicate it with each other, that is because of partition, network partitioning. So what is network partitioning? I mean, in two nodes, it's kind of like very simple, but if I show you another picture, let's say you have 5 nodes, they all are connected to each other, let's say in this fashion. So if at all, let's say this connection is broken, and this connection is broken. So now you have kind of like two partitions in this network. So one partition, earlier you had a cluster with 5 nodes. Now you have a cluster with 2 and 3 nodes. So there are two partitions, separate partitions in the cluster. So that is what is network partitioning. So coming to partition tolerance, what it is saying, uh, when there is network partitioning, as we talked here, so if this link is broken, now there are two partitions, one with each node, or in this example, two partitions, one with 2, one with 3. So in the CAP theorem for partition tolerance, saying that when there is a network partition, you should have tolerance to that network partition, because network partition is something that can always happen in any distributed system. And in that case, a node should be allowed to drop messages when partition happens. So your system should be able to cope with partition tolerance by dropping message. And then you have choice between either choosing consistency or availability. So like if we go back here, we are saying that uh, when this link breaks, we can either accept the write request and then make sure that until that write is replicated here, then this server is no longer available to serve the client's request, which means we are sacrificing availability. Or we can say that we'll take the write here, whenever this is back, this write will be replicated here. And in the meantime, clients can either go to server 2 or server 1. What answers they will get might not be consistent, but they can still serve the question. So you could, let's now go back to a practical example of how, if you were to sacrifice consistency or availability, i.e. if you say that, okay, I will let this client, let the clients go to server 2, how you will design your system. So by the way, when we'll talk about various databases, moving on from SQL to NoSQL, we'll talk about some of the databases have ability to prefer availability over consistency, like Cassandra. It goes for availability over consistency. It allows you to tune your consistency, where other databases, they prefer consistency over availability, like MongoDB. So we can talk about all those things. But let's say if you were to prefer availability over consistency, what you will do here. So what you will do is you will accept the write here, you will accept this row here, will try to replicate, but it won't, but that's fine. Why that's fine? Because your response would be something like this. Whenever a query comes in to say how much a person A owes to person B. In this example, how much Chris owes to John. So if after these two rows are written here and only one is available here, when the query comes in here, your response will be uh, Chris owes 40 pound uh, to John on 3rd of Feb 23. And when you ask the same question to server 2, you could answer it in a way by saying that Chris owes 100 pounds to John on 31st January, right? So if you think about it, what you are doing here is you are letting your nodes be available to serve the client's request. And based on the latest information that these nodes have, they are serving the client request. And that information is, by the way, not wrong at that point of time or in that context, let's say. And you are, in that sense, achieving for what is called eventual consistency. So eventually this information will be replicated and then it will get the latest information. But in the meantime, based on latest information that it had, it is serving the client. So again, Based on the scenario, this may or may not be the right approach. Eventual consistency may or may not be the right approach. But going back to the CAP theorem, what we are saying is when in a distributed system, network partitioning will happen, then you should have partition tolerance by which your nodes can drop messages when the two nodes cannot communicate. So messages between them can be dropped or information shared between them. Let's not use some messages and to confuse some other technology here. What we are saying is information that needs to be communicated between two nodes. That information communication may not have when network partition happens, then that information communication may not happen. And in that case, you have to choose between consistency versus availability. So the node that have the latest information, is that the only node that serves the client and others don't? Or you say that we will let the other nodes also serve the clients, but then the will not have the fully consistent state with the one which has got all the information. So this is what the CAP theorem is about making sure that you understand what compromises makes best sense for your architecture when you are creating a distributed system, when you are designing a distributed system. So based on that, you can say what is more suitable to solve your use cases. Hopefully that provided some insight into what the COPE theorem is. It gave you an idea of what are the challenges that you need to take into account when you are designing a distributed system and what are some possible ways to look into those channels. Thank you.